Hey, this is Steven from RC Engineering, and welcome to my Rule of Thumb series. This is my January Rule of Thumb. We're going to have 12 this year, one per month at the very end of the month, very last week of the month, and we'll be doing 12 altogether this year. So this one is number 1, obviously, this year, and let's go ahead and get into it. So we're going to be doing a plain one for this month. And we're going to be talking a little bit about propellers. So in order to learn more about propellers, you kind of need to know what a wing is, but we'll go into its own video to talk about wings and some of the factors having to do with wings and some basics of aerodynamics. But in this one, we're not going to go too deep into it. Later on, we could attach those two knowledges together to get a better understanding, but I want this video to be quicker. And I actually just did a recording where I had that in there, and it lasted 10 minutes just by itself explaining what lift is. So I'll have that in a completely different video. Okay, so we're here on my computer. Sorry, I don't have my laptop, and I can't do it on my laptop because I don't know what I did with my stylus. I'm going to have to order another one, or if I find another one before Sunday, I'll redo this on my laptop because it's way better on my tablet. And then I could use my stylus. But right now I'm going to be doing it on my desktop PC, so if I'm probably going to be drawing some stuff in Paint, so if I need to draw stuff, bear with me. It's using my mouse. Okay, so we're going to be using this particular document. It's called Model Airplane Propellers by W.B. Garner, March 2009. And we're going to be going over, this is just a small little dip into it, but it's still going to be a long time going over it, but I think that this is a really great document. So we're going to go with Synopsis, Section 1, Physical Properties, Section 2, Performance Properties, and Section 3, Normalized Performance Relationships. Section 1 is just talking about what a propeller is and why it's shaped how it is, which we're going to go over. Section 2 is talking about elements of force relationships, concept of propeller wind, and how it relates to angle of attack that produces thrust. Number 3 is basically some equations and graphs that we could use to match our propellers to our planes as far as how fast we want to go, what kind of motors we have, how to get maximum efficiency, what type of thrust are we going to get, how much power do we need, etc., etc., etc. Actually, during flight. So this is where we could apply a lot of rule of thumb knowledge. And these rest of these we'll be going over later. So we're only going to do Synopsis Section 1, 2, and 3. So let's go ahead and get into it. So here basically what it's saying is that our propellers on our airplanes are not the same as propellers that are on actual airplanes, because actual airplanes that have propellers have generally they have adjustable pitch. So they'll have mechanics inside the propeller that will allow it to rotate the blades to match the pitch. Ours is pretty much just kind of a more dumbed down version where it's just a solid propeller. There's no moving parts or anything like that. In here it's talking about, this is a basic wood propeller, but very similar to our plastic, and also our fiberglass reinforced, our ABS props, or our polycarbonate props are very similar. So what it's mentioning here is that it goes from a very wide hub here, very wide and thick hub, to very, very thin blades, and they taper as they go off, which we'll go over here, but it has to do with the strength that's needed and where the strength is needed to lower weight. And it's also mentioning, very important, that it's twisting along, it's periodically twisting more and more along its length, and we'll have to go into Paint here to show you guys that. In order to understand the shape, it is useful to know what the purpose of a propeller is and how it accomplishes this purpose. The primary purpose is to convert engine power to actual thrust. So what it does is it's rotating on this axis while it's creating a thrust upward to propel the propeller forward. So basically you're turning rotation into linear movement, into straightforward movement. So converting rotation to straightforward. Same exact thing as a car. You're creating, you have an engine, it's rotating a shaft that goes into a differential that distributes it to the wheels, and then those wheels rotating are going the same direction as the engine is rotating, on the same axis. Actually, if you go through if you put a dart right, or if you put a stick right through the engine, you're going in the same direction the engine's going, right? Even though the engine's rotating. So you're turning rotating movement, continuous rotating movement, into forward movement in the direction you want to go. So it's saying engine power to actual thrust via torque transfer, rotational force to the propeller. Thrust occurs as the rotating propeller captures air, a fluid, and accelerates it and pushes it out the back. And the act of accelerating it from a slower speed to a faster speed is what gives us our thrust, because that generates a force, and a force accelerates our plane in a certain direction. The more air it expels per unit of time, the more power converted, and the greater the thrust. In order to push the air, it must be able to capture or grab the air. If the blades were flat, no twist, and orientated perpendicular to the direction of flight, they would not capture any air. The flat blades would be tilted, so they bite into the air. This works after a fashion, but is very inefficient. So the blades are twisted to improve the efficiency. Figure 1-2 illustrates what happens to a blade when it is twisted and moves forward for one revolution along the z-axis. So what you can't see here is that this one right here is a very large angle, and then it starts to get to more of an acute angle. So let's go ahead and show that here. So let's say that you have an axis, right? So this is our Cartesian axis. So let's say this is the flat plane. So this is perfectly flat. So if the blade had no twist. So at the very start of the blade, you'll have something that's maybe like that, right? And then as you get along the blade, you'll actually see that it starts to flatten out. And also it starts to get smaller. So as it goes down the blade, it starts to flatten out to the point where near the end, it could be near flat, right? Oops. Okay, so, yeah. So the objective is to make each piece of the blade along its length advance actually the same distance in one revolution. So that means that, I'll show you guys what exactly that means in a second, but its changing according to its radial rotation, its radial speed. So here it's basically saying in order to maximize lift and minimize drag, the designers have found a ratio of a 7-to-1 length to width ratio. Reason being is that the wider the prop is, the more area that the air has to interact with the blade, which causes drag. The more the air is attached to the blade, the more drag is induced by friction of the air against the blade. So by having a 7-to-1 width ratio, you don't have too much interaction and don't have too less, because you still need the air to interact with the blade in order to generate thrust. And another reason for thickness and width tapering is mechanical. So basically what it is saying is that most of the stress of the blade is happening at the center hub. And then as the propeller tapers out, you need less and less thrust, because you need less and less strength, because there's less and less thrust being generated at that portion. So here you have a lot of blade left that's generating thrust. Here you have less. Here you have less after a certain point. So the farther you go from the hub, the less thrust is generated and the less strength you need, so you could compact that blade. And the other idea why blades are gigantic, again, is because of the drag, and number two is because when you have a rotating mass, when you try to accelerate very quickly on a propeller airplane, especially an RC airplane, it takes some time to spin up to speed. Now the heavier to change its speed, the more mass it has. Force equals mass times acceleration. So acceleration is a change of velocity. So if you want to change the velocity very quickly, but you only have a certain amount of torque, and torque is a force, right? So that's your acceleration. So if you only have a certain amount of torque and you want to change speed faster, you're going to want a lower mass. And a heavier mass prop is not going to help you generate more thrust. So generally you want to minimize mass. Number one is because you have to fly that around with you, right? You have to pick up that weight with lift from the wings. And number 2 is you have to accelerate by speeding up that rotation. So here it's talking about while 2 blades, you can have planes with 3 or more blades. Since 3 blades have more lifting area than 2 blades of the same size, the blade length can be reduced somewhat while maintaining the same forward speed. So basically the swept area, the whole area of the circle that the blades are sweeping, you're going to have more blades taking up more of that area. So you could actually make it smaller to have the same amount of area swept at once. So blades that are taking up that area. So you could actually adjust, and it has a few calculations in here of how you could adjust for if you have a 2-blade prop but you want to go to a 3-blade prop, what is that equivalence? So here's talking about how propellers need to be balanced, and what happens if your hole is not perfectly in center, if your prop is not manufactured correctly. So here, as we know, propellers are defined in terms of their diameter and pitch. Both are written on the blade. Sometimes they're in inches, sometimes they're in millimeters. So the diameter is the total diameter of the blades, which is the total length of the blades. And also it's the diameter of the circle that is swept by the blade tips. It's in either inches or millimeters. Now this is a pretty interesting chart here. This is talking about what... how long down one side of the blade, not the whole blade, but one. So if you have 2 blades, one blade, which is the radius of the circle swept, where is most of that thrust developed? As you see, as the further you get down the blade, because here's 80%, so that means that this is the thrust. This area under this curve is the thrust that's generated along that blade. So here, this is 100%. So you're saying from here to here, you have 40%. 40% of the thrust is generated at the last 20% of the blade. So at the very, very edges of the blade, you're generating massive amounts of thrust. And the closer you get to the hub, you're generating very little to no thrust at all. And then you see from the same distance from here, 60 to 80, you're generating 20% of the thrust, and here from 40 to 60 you're generating again about another 20% of the thrust. So as you can see, not much there, but here gigantic amount, because as you see it starts to accelerate. So here it's basically saying that the rating of the pitch is rated at 75% of the radius, and the pitch, I don't know if it's the pitch of a blade is basically the linear distance, or the forward distance that the blade will, that the whole plane will travel with the blade attached, right? We could also think of we're just going to disconnect the plane from it and say the prop. So the pitch is the measurement of inches or millimeters that the propeller will move forward if in one rotation. So if you have a 6-inch prop, let's say 6-inch pitch prop, in one rotation of that prop, if you had no slip and no losses or anything, your propeller should go forward 6 inches in one rotation. So if you have a very high speed prop, you would think 6 inches times whatever RPM your motor is. That's how fast you should be going. That's your relative speed. So that's what a pitch is how far forward the propeller will travel in inches or millimeters per one revolution. So it says about 80% of the thrust is generated by the outer 50% of the blades. Since virtually no thrust is generated on the hub can be designed for strength. Spinners do not appreciably affect the thrust, but do reduce drag of the engine area. So although most model props have 2 blades, there are versions with 3 or more blades. So there's a basic equation here. dn is the diameter of a propeller of n blades. So let's say I wanted to go from a 2-blade to a 3-blade. So this would be the diameter of the 3-blade that I'm going to substitute for the diameter of the 2-blade, which is d2, the diameter of the 2-blade, times 2 over Bn. Bn is the number of the blades in the end blade prop, so let's say 3 blades. So the diameter of the 2 blade that's currently on the plane, 2 over the diameter over the number of blades that are on my new one, so let's say 3 times 1/4. And so that will drop the blades. So here you go, for 3 blades it's approximately 0.904 times the diameter, and for 4 blades it's 0.840 times the diameter of the original. And here's a 2 blade, you can see the 3 blades smaller and the 4 blades even smaller. So also the aerodynamic influence of additional blades reduces the power consumption by a small amount, which means that the replacement 3-blade prop will consume slightly less power than calculated above. On the other hand, it will operate at lower Reynolds numbers, so some additional losses can be expected. We're going to go over Reynolds number later. Now this is part 2, which is a very important section. So while a propeller is a physically simple device, its performance characteristics are complex. There are 4 performance parameters named thrust, which is what we want to maximize, thrust power, PT, torque, which is a measurement of your motor, and shaft power, which is wattage of your motor. Consider alone performance as a function of diameter, pitch, RPM, forward velocity, otherwise known as your flying velocity, how fast is your plane flying, and airfoil shape, and dimensions, characteristics by lift, CI and drag, CD coefficients, propeller, blah blah. So this, I'm going to talk about this picture for a second. So this is a picture of a propeller, and these are some very important numbers. So this is going to be talking about how the pitch of the blade is calculated. So here V, as you know, V is the forward velocity of the plane. So how fast is your plane flying? 30 miles an hour, 40 miles an hour, 50 miles an hour, 60 miles an hour. Now this here, it says 2, let's just say 2 pi r, 2 pi r RPM. So basically it's 2 pi the radius times your RPM. So it's basically the spinning speed of your blade, right? So you have this velocity times the spinning of your blade. And then this is theta, and theta is the angle pitch, otherwise known as the pitch of your blade. And then alpha is the angle of attack, which is how much additional angle are you going to add just to get some extra lift out of that blade. We'll go over that later, but this is very important. And then beta, that's a B, beta, which is alpha, which is theta plus alpha. And then this is relative velocity in a certain direction. So let's go, see 2 pi rn, where r is the radius at where you're trying to figure out the pitch, and n is the RPM. So I'm going to go over how that's calculated. So here is kind of a diagram of showing, so here is the wind that's hitting it, but here's VR, and this is VR right here. So it's saying the farther out you go, the faster the VR is. So this is how this is calculated. So this is how the pitch is calculated. So you have an angle, and this is known as trigonometry, right? So let's say there was no angle of attack. Let's say that the blade was exactly how it was calculated. So here is my forward velocity. So this is my speed going forward, right? So let's say I'm going 20 miles an hour. Sorry, this is very hard. It's very hard to draw with the mouse. Okay, so I'm going forward at 20 miles an hour. So M P H. So I'm going forward at 20 miles an hour. So now let's say that I'm looking at a space of, obviously the units aren't going to work out, but so let's just say that we're going 2 feet per second. So we're going 2 feet per second, and we're going to look at a blade. We're going to look at the tip of the blade. So we're going to look at 1 foot. Let's say we have a blade. Let's say we have a piece that's rotating at, let's say we have a prop that's rotating at 10 RPM. So this radius, the blade's radius is 1 foot. Total blade size is 2 feet. So one blade's 1 foot long, 2 feet diameter. 2 feet dia, so 1 foot radius. So we have 2 pi r, which is radius, times the number of rotations, which is 1,000, let's say 10 RPM. Okay, so we have 2 pi r and then times rotation. So 2 times r is diameter, so we could say 2 times pi, and pi is 3.14, so we're going to say that's 6.28 times 10, so that's 62.8. So 62.8, and then this is feet per minute. And then you're going to divide that by 60, so that's around 1 something, 1.01 or something, feet per second. Okay, so this is 10, and this is 2. So this is trigonometry, so what you'll do is you'll do a tangent, an inverse tangent of 2 over 10. So this is what you would type into your calculator. We'll go over this quite a bit later. Tangent inverse 2 over 10. And then this will give you a degree angle. And that degree angle is the pitch at that location of the blade, flying at 2 feet per second and rotating at 10 RPM at 1 foot down the blade. And you would do this in increments down the blade to generate a blade pitch, and then that would be your correct blade pitch. So we'll go over how more of this is done later on. Okay, so as you can see, as you go further down the blade, this is rotating faster because of the distance away from the center. Because we have 2 pi r, as r increases, even though we're spinning still at the same RPM, no matter where you are on the blade, you're still spinning at 10 RPM. That doesn't change. So this doesn't change, but when this changes, this increases. And when this increases over this one, this pitch gets lower. And so kind of what this does is when this pitch is changing, it's helping with the wind. When the wind comes here, the wind is actually grabbing onto the blade and helping you rotate the blade. So it's actually helping you spin the blade around. So in the center of the prop, it's not very useful for thrust, but you'll see on a lot of the faster airplanes, they have a very almost parallel to the direction of travel pitch on the blade right there, and that is for the speed. That is for the wind to help rotate the blade, so you could generate even more thrust. So it's basically saying how much of the air is going to help generate thrust at the rest of the blade than how I'm actually rotating. So towards the end of the blade, when you're generating the most thrust, you're spinning way faster than the air is hitting it, because the air is does not change at 2 feet per second. So RPM does not change and wind speed does not change. So as it's hitting your plane, that airspeed is not changing, RPM is not changing, but your speed along the radius of the propeller is changing. So that's why you have that twist as it goes out to the end, because at the end it's spinning really fast compared to the center, and it's generating, as it says, 50% of the thrust, 80% of the thrust past 50% of the blade. So very, very important to have the right blade pitch. And again, when you buy a blade, the pitch is rated at 75% of the radius, right? It really depends on the company, I'm sure. So here you have the wind, right? Propeller wind. And we're not really going to go over this, but it's basically saying how much speed is generated. And the longer the line, the more speed is generated. So here is just wind speed. This is the center of the hub. This is just the wind speed hitting the prop. And then here is actually the wind that we're accelerating. And as you see, we're accelerating way more the further out we get from the blade. But right here, it's going to help us a lot with helping to spin the blade. The air is actually going to help us spin the blade. So another property of propellers can be derived by examination of figure 2.1, which is the angle of attack, similar to that of a wing. As it decreases the lift, in this case the thrust decreases, eventually becoming 0. So you want this additional angle of attack, which is also pretty important. Which I'm sure they have a standard for that. Assuming for a moment that the RPM remains constant, so 2 pi Rn, the horizontal wing component remains constant, an increase in forward velocity decreases alpha, thereby, and this is angle of attack, thereby decreasing the thrust. The thrust becomes 0 when V equals NP, which is rotation times the pitch over 1056 miles per hour, where N is RPM and P is pitch in inches. Thus, to achieve maximum speed, increase RPM or pitch, which is pretty obvious. Okay, so now we're going to go into, so this is the angle of attack. So this is what kind of alpha you would add to get beta, which is your total angle here. So you would use this to calculate this here will give you theta. And then theta plus alpha, I'm going to do lowercase alpha, is equal to beta, right? Which is your total angle, which is this angle. And then you're going to use this chart right here to figure out the alpha, which you're going to add to beta. You're going to add to theta, you're going to add alpha to theta and get beta, which is your total angle. And then so to use this chart, you have here blade angle of attack, which is the pitch divided by the diameter of 0.5. So this is a what they call an indoor prop. You'll have this right here is R times diameter. So where are you looking along the prop? So let's say we're looking at 1 inch along a 5-inch prop diameter, or let's say 10-inch prop, 10-inch total diameter but 5-inch radius, and we're looking at a specific radius of 1 inch, then that's 1 divided by 10, so that's 0.1, so that's this blue line. And then here we're looking at the V over ND, so what is your wind speed compared to your speed of diameter, so N times diameter, which is 2 pi R, right? Or in this case without the pi. So V divided by ND. And then you can see here that it says down here, the angle of attack is illustrated for pitch diameter ratio of 0.5 with RD. The radius along the blade divided by the diameter is a parameter. The ratio V over ND is a measure of the horizontal wind angle. The blade will stall at an angle of attack of around 15 degrees. So that is this angle of 15 degrees. It will stall, which again, alpha is actually alpha's right. Alpha's right here is this angle. So when this gets more than 15 degrees compared to the wind, your wing will stall and you'll start to lose lift or thrust in this case. For this case, most of the blade is not stalled, even to small values of V over ND. As this value of V over ND increases beyond 0.5, the attack angle becomes negative, meaning that the propeller is actually being pushed rather than pulling. So you're actually not even generating anything. You're negative thrust, pretty much. You're going the opposite direction. And then this next one is an angle of attack. Illustrates what happens for a high pitch propeller. In this case, most of the blade is stalled at low VND that typically occurs at high RPM and low forward velocities, such as takeoff. A plane equipped with such a propeller is likely to be initially sluggish on takeoff, but can fly faster than the lower pitch blade. So this is going to be your higher speed plane, and this is your lower speed plane. This is like your slow indoor flyers or slow outdoor flyers, aerobatic, like 3D planes are going to have this. This is the pitch is 0.5 over diameter. So let's say you have a 6-inch prop, so it's going to be a 630, 0630. So 6-inch prop, 3-inch pitch, right? So pitch is going to be half the diameter. And then here is a full speed prop, which your pitch is the same as diameter. So if you have a 6-inch prop, it's a 6-6 prop. Right, 6-inch pitch, 6-inch diameter. Alright, finally, part 3. We're going to go through this pretty quick because we're going to go a lot into detail on this later on. So here it's talking about no simple relationships, but there are some things that they've done multiple, that they come up with numerical models for by doing a whole bunch of testing to generate these models. So we have a few different things. We have 3 mainly: thrust coefficient, CT, power coefficient, CP, and the efficiency coefficient, which is N. All definitions in terms of a variable called the advance ratio, J. The advance ratio is your forward velocity divided by N, which is your RPM, times the diameter. So N is revolution rate, D is diameter. Now, a thrust is given by equation 3.2. So thrust is equal to the thrust coefficient times the density of air times the RPM squared times the diameter of the blade cubed. So here, density of air is equal to 0.002378 slugs per foot cubed. And we're going to go over a online calculator that I made for these calculations to calculate different blades for different planes. And here is a plot of how you find, so you're like, okay, how do I find CT? CT, you have to go to this chart here. And this depends on your advance ratio. So your advance ratio, again, is J over V over ND. So what I'm looking for, let's say I have, this also, again, is P times D. P over D. So what is your pitch? Same thing here. Not that one, but I think it'll tell you down here. Anyways, yeah, right here. Plots of the thrust coefficient as a function of J and PD. So these lines are different PD ratings, and the J is the advance ratio. So PD, your pitch divided by diameter. The ratio of the pitch to diameter for a typical model airplane propeller profile. So if you have a, let's say like a 5-inch diameter by a 45, then that's like a 0.9. So you'd follow this line. And then your advance ratio is your wind speed, your forward speeds, 15 miles an hour, 17 miles an hour, 20 miles an hour, divided by N times D, which is your RPM times diameter. So down here they have an example, and we're going to follow their example. So it says here, maximum thrust is achieved at the lowest advance ratio, decreasing essentially linearly as 0 to 0 as J increases. The values are not reliable in the region at top, blah, 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 blah. The greater the pitch ratio, the larger the range of J affected by stalling. Also, these curves go to 0 as J increases, meaning that the thrust also goes to 0. The underlying reason is that the angle of attack A becomes 0, so the blade does not provide any lift or thrust. Using this chart and the equation for J and CT, the thrust can be estimated for a given set of conditions. For example, you're flying at 60 miles an hour, 88 feet per second, and you're spinning at 12,000 RPM, which is 200 revolutions per second. And you have a diameter blade of 1 foot, otherwise known as 6-inch prop on one side, 6-inch prop on the other side. So 6-inch radius, but this 1 foot prop, or 12-inch prop. And so your pitch is, this is diameter times 0.7. So that's that's an 8.5 inch prop. This is an 8.5 pitch prop. So 8.5 by 1 foot. 8.5 by 12. So you calculate J, which is V over ND. You're traveling at 88 feet per second divided by 200 revolutions per second times 1 diameter is 0.44. So now we have to go find CT. So we're going to look at this PD is 0.7, and we're going to look at 0.44J. So 0.7 the blue and 0.44J. So we're going to look up here. That's about 8.08. I think I used the wrong ones. 0.7 PD. Yeah, 0.44. Yeah, 0.09, something like that. I don't know why they use 0.056. Anyways, I don't think that's correct, but alright. So T thrust is equal to CT, which is what they found, 0.056 times the density of air times the RPM squared times diameter cubed. And so they have 5.3 pound force of thrust. And then now we have the engine shaft power. The engine power required to produce the thrust is given by equation 3.3, which the engine shaft power in horsepower is the power coefficient times the density of air times RPM cubed times diameter to the fifth. So again, is a function of J and the pitch diameter ratio for typical sport propeller. So here again is P times D, P over D, which is pitch to diameter ratio, and over the advance ratio. So you can see we have like a peak here in the middle range, and we'll go through one of their problems. Continuing the example used for the thrust, for J equals 0.44, P over D equals 0.7. We're going to look from 2.5, 0.7 PD, 0.44, 0.44, 0.7 is the turquoise, or the kind of blue. So we're looking at 0.045 or something. I don't know why they can. They're looking at like a completely different chart. It's almost like they must have not remembered what they picked here. Anyways, so 0.034 times the density of air times the RPM cubed times the diameter to the fifth divided by 550 is 1.17 horsepower. So you could generate 5.3 pounds of force with 1.17 horsepower, otherwise known as probably around 830 watts, because there's 750 watts per horsepower. The very last thing we're going to go over is efficiency. Of interest is the power efficiency. So how efficient is this prop? And so the general efficiency equation is CT times J over P. So your power, so you want to minimize your power coefficient, right? But you want to maximize your thrust, and you want to maximize your J, because J is wind speed. So the faster you fly relative to your RPM, and the lower and the higher the thrust you get, the better your efficiency is. And so here is the chart, and then this is in the function of J and pitch and diameter ratio. So as you see here, we can get a maximum efficiency of about 80, 83%, 85% efficiency, and you can't get any better than that on a propeller. And you see here with all the different P to Ds, you could get different efficiencies. So in our example, for J is equal to 0.44 and PD is equal to 0.7, the efficiency is about 73%. So let's double check. It's probably wrong again. 0.4, 0.7. 0.7 is turquoise. Yeah, about 73%. I agree on that one. That one's right. Over most of the in-flight operation values for J, the efficiency is about 50% or greater. Alright, so that is the basics of what we're going to go on, and maybe one of the later videos I'll definitely be going into lift, and we'll be going into generating a calculator so we could calculate what types of props for different types of environments that we want to run. You know, we want to run a slow plier, or we want to run a really fast jet, or a prop driven airplane, or we want to go from 2-blade to 3-blade, or 2-blade to 4-blade, or anything like that. What kind of propeller do I need, and what type of pitch, what kind of diameter, what type of motor do I need, match the motor, maximize motor efficiency. So we're going to start to combine propeller efficiency with motor efficiency curves, and then create a really smart calculator to do that. So this was kind of just like a rub into this type of calculations. Maybe we'll do some more calculations on this in another rule of thumb series, or I might add it in to this week to do some calculations as well, so we could really cement this knowledge here. But this is the basis of a whole bunch of stuff that we're going to be doing, and I use this quite a bit now to find efficient props and to also see guesstimate what type of motor I'm going to need, rather than going online to Google or YouTube to try to find some static thrust analysis of people running static thrust tests to see what their propellers are doing. So with this, I'll be able to predict how the prop will perform in the air, and also a relative speed of how fast the airplane will be going. So we'll be talking about this topic quite a bit more, obviously a whole bunch more, because I'm big into airplanes, drones, and helis, and also we'll be going into other topics of cars and boats soon. And also this applies quite a bit to boats, because also water is applied as a fluid. You could just change the density, instead of air, density of water. Alright, so this has been Steven from RC Engineering. I hope you guys enjoyed my probably very long video of my rule of thumb series for propellers. And if you haven't done so already, please subscribe for more videos like it, and I'll see you guys in the next month's rule of thumb series. And if you guys would like to check out some other free content, go ahead and head to my Patreon, link is in the description, and for other free content there. I'll see you guys in my next video. Thanks for watching. Take it easy. Peace.